Thank you, Marco. Welcome back after the coffee break. Is Professor Desai here? Yes, I can see him. So it's really my honor to chair this last lecture delivered by Professor Chandra Desai, a scientist and I would say a still researcher, for he still devotes so much of his time and his passion to research. Professor Desai doesn't need actually to be introduced. We all know him very well, especially all the community of this international association, who he contributed to found many years ago. So it's really my pleasure to leave the floor to Professor Desai, and thank you in advance for the lecture that we are going to enjoy. Please, the floor is yours.
My presentation is here, I can see, but please tell me, okay.
Okay.
All right.
Yeah. If you switch to presentation mode, then it will enlarge.
Oh, okay. Okay. I can start now. It is about 8 o'clock here. Luckily, I was on the web, your system for last 40 minutes. So I watched some of the other things. First of all, I want to thank Marco and the organizer to asking me to give this lecture on this special technological occasion of breakthrough of doing this on the website. I'm very impressed. Marco and your group has done excellent and outstanding work for organizing in this difficult time. And I hope, maybe wish I can come next year. Before I start, I want to express my memory for my friend Giovanni Barla, who was a friend for a long time, and I can dedicate my lecture to Giovanni in his memory. In 1972, when can you listen to me?
Yeah.
Are you listening?
Yeah, we can hear you.
And I'm also in 72, when we started this small conference series, there was not a single woman. And I'm very impressed this time that we are so many women participating in this conference. We try many times, but I'm very, very glad, and young people and women. And I thank also Donatella. I have not met for a long time, for introducing me. I'm going to talk about the important topic of liquefaction. And liquefaction has been researched and applied for a long time in geotechnical engineering and geomechanics. Starting from Professor Seed, liquefaction has been defined from some laboratory tests and field tests. But when I did some work a few years ago, I thought liquefaction was a phenomena which occurred inside the material because of its particle and microstructural conditions. So external definition by SPT, standard penetration test, has been useful, but to define in a fundamental and basic manner, I think you have to consider liquefaction as a phenomena which occurs by microstructural conditions in in the material. So I want to divide, I have about 40 minutes, I think, and I will try to finish by that time. Microstructural instability, liquefaction in geologic material. I consider liquefaction as one of the instabilities which occur inside the material microstructure. And then a disturbed state concept, which I have been working on for modeling material and interfaces, and I will present some field and laboratory validation for this approach. See, we consider material, the material particles are joined together with friction, adhesion, and also the gaps are filled with water or air. When this material microstructure is subjected to loading, in my opinion, this is a guess, that actually the material particle movements are also oscillating, that it actually behaves in a somewhat sinusoidal or some irregular manner. What we measure outside in the laboratory test is the average of that oscillating behavior. During this time, those oscillations sometimes become spikes and breaks, and instability occurs. All instability do not cause failure or liquefaction. Only some of the instabilities cause liquefaction. For instance, here we have a stress strain curve, and somewhere here, what I denoted by disturbance, that volume change occur. That is a sort of an instability, but it doesn't cause any failure or liquefaction. Then there is a disturbance at the peak value. The peak value is also sort of instability because it is sort of a neutral equilibrium there. And then somewhere at this point, a critical disturbance occurs when liquefaction or failure can initiate. And at the end, total failure can occur. So all this is result of the internal readjustment or reorganization of the particles. The distinct material, not only there are particles, but it contains initial and induced discontinuities. And these discontinuities also participate in inducing unstable state of the material. In this paper, we will concentrate on liquefaction instability as a special case of this threshold state, which I consider unstable state. And for fundamental approach for modeling liquefaction, the internal mechanisms are significant. The disturbed state concept and energy approaches are capable of accounting the internal mechanisms. In this paper, we'll briefly describe energy approach, but we think that the disturbed state concept is emphasized here because it provides simpler and more direct modeling for liquefaction. I mentioned in the beginning the conventional approaches developed by a Berkeley group, Professor Seed and everybody. And they, I think those are based on, for instance, standard penetration states, cyclic resistance ratio, but although they are useful, but they are essentially external and do not relate to the internal mechanism that cause liquefaction. They are external. You touch the material externally and say what is happening, but inside what is happening requires fundamental consideration. So energy approaches have been used and they are basic and like DSC, but they are somewhat difficult to compute, in my opinion, for liquefaction. See, there is once in a paper, sometimes few years ago, I connected energy approach and disturbed state concept. If you plot the disturbance here with a number of cycles and a disturbance, a critical disturbance occurs here and liquefaction curve. Similarly, if you plot energy versus number of cycles and you find a corresponding critical energy density. So it is possible to do that. I don't want to go into detail, but the material experiences elastic plastic strain affected by initial conditions, stress path, volume change, micro cracking, and microstructural instability and loading and rate of loading. But many of these above feature can occur simultaneously in a material. They occur simultaneously and they are coupled together. And many conventional models don't do that. They do specific factor or one or two, while disturbed state concept can allow all these factors, including microstructural instability. There are so many models, elasticity, plasticity, creep models, and we have, I will discuss briefly hierarchical single surface plasticity, which is integral to the disturbed state concept. And also micromechanics, some papers are there, fracture. But all this have some limitation, and we think that this disturbed state provides a unified approach for, okay, let me skip some, okay. It is, as I said, disturbed state concept is based on internal microstructural modification, including particle motion, threshold state, and instability resulting. That is captured by the disturbed state concept. Let me see here. See, in a brief, microstructural changes may involve directional microcracking, but it can be defined in an aggregate and weighted manner. So disturbance in the disturbed state concept represents a weighted sense, the effect of microstructural modification, such as instability. In a weighted sense, it is not a directional or vectorial sense. Through irreversible deformation or strains or work, plastic work. Well, I don't want to go too much, but in my book on disturbed state concept, I discussed that in a philosophical sense. In Chinese philosophy, and this is Indian philosophy, when material behavior is material matter in the universe is composed of two systems. Something exists, something doesn't exist. But they exist together and merge, combine it each other. In the same manner, the material behavior, material can be composed of continuum and discontinuum, like existence and non-existence, which are coupled together, can merge into each other. And that is based on microstructural modification at the particle level. Sometimes in a continuum behavior, we define stress at the point. But when a discontinuum material occurs, discontinuity occurs, micro-cracking occurs, damage occurs, at that point, that definition is no valid, because the behavior at the point is also affected by what is happening in the neighborhood. So, disturbed state concept, the stress is defined in that manner, in a weighted sense, affected by what is happening surrounding it. I don't want to go, there are so many other methods. One of the advantages of the disturbed state concept that it can be, it is main mathematical framework is applicable to both solids and interfaces and contexts. You don't have to define mathematically other way. Both can be defined by the same mathematical framework. And this is a unique and significant advantage. The basic idea, as I mentioned philosophically, is material is composed of relative intact of continuum state, which its behavior is manifested, means it can be measured, and fully adjusted state when the material goes from the continuum to the total discontinuum state or disturbed state. That is called fully adjusted. So behavior of the material now in disturbed state concept is defined in terms of the behavior of the relative intact of continuum part of the material and discontinuum or fully adjusted part of the material. This is a CT scan of a mortar specimen near the peak of the stress in a triaxial test. And you can see that the CT scan, computer-aided tomography scan, gives you materials is in two parts, white part and black parts. And the black parts are sort of near fully adjusted state, and white part are a continuum state. And the behavior of this material can be defined relative intact or continuum or fully adjusted part, if you can define it. And we have found that disturbance can be defined as the volume of the material in the black state and volume of the material in the total volume of the material. And that is a disturbance. And that relates to the internal behavior. In a stress-strain curve behavior is like this. and their disturbance is difference between the relative intact continuum part and the actually observed behavior. That is a disturbance. There are two reference states: continuum RI behavior and fully adjusted behavior. Between these two reference state, there is the behavior, observed behavior. And the observed behavior then can be expressed in terms of the behavior of the continuum RI state and this fully adjusted state. This is very simple, like physics principle. The behavior of a mixture can be expressed in terms of the behavior of the component of the mixture. That is a basic, simple principle. And the stress, actually stress now is defined not only at a point, but it is defined in terms of the disturbance, stress on the continuum part, stress in the discontinuous part, and the extreme strum for stress in the critical state and the intact state. If disturbance D is 0, this represents a continuum behavior. But if the disturbance is not 0, then it takes care of the discontinuities, and also I will say failure or liquefaction. The hierarchical single surface plasticity can be used at one of the model for the RI behavior. And that model is described by the yield function in terms of the invariance of the shear behavior and mean stress and number of parameters. This model is so general that you can derive all the conventional plasticity model like Moore-Coulomb or Drucker-Prager and critical state from this behavior depending on the parameter value alpha and gamma and beta. So this is a general plasticity model which can be used for the behavior of the, it plots in a continuum, hierarchical single surface continuum sense. I cannot go into details because of the time limitation, but this behavior include critical state as one of the special cases where phase change occurs. Fully adjusted state. You can assume the fully adjusted state has a 0 strength, but it is not good. It gives to uncoupled behavior. You can assume like a bulk modulus, that classical plasticity. This is a, I'm sorry, this is like a damage approach. It is not good because it doesn't give a consistent behavior. Liquid, like classical plasticity, you assume the fully adjusted state defined by the bulk behavior. Or critical state, you can define just like this as in critical state model. You can find in partially saturated soil, saturated state as a disturbance can be expressed in terms of the stress strain behavior, ultrasonic or non-destructive velocity, or just strain or pore water pressure in a saturated material, or in physics entropy. It has been done by all these methods. Disturbance can define entropy. And for instance, stress strain behavior, volume change behavior, velocity, ultrasonic velocity, shear velocity, or pore pressure behavior. You can define disturbance in this sense. Like also in cyclic behavior, it can be defined as an initial behavior and the observed behavior, and the critical state here where liquefaction occurs in cyclic behavior. It can be, it's also expressed in a general mathematical stand as a ultimate disturbance and two parameters A and Z, and plastic work or plastic strain trajectory. Oh my God. If you plot disturbance or strain or number of cycles, it will plot usually like this. For softening behavior, it can be like this. And stiffening behavior, I forgot to mention, but disturbed state concept also consider a stiffening behavior. But sometimes material, because of the temperature or chemical reaction, is stiffens, it forms a softens. And that also is considered in the disturbance. Very, very briefly, I want to go to the capabilities of the disturbance. Very number of materials you can apply: sands, clays, rocks, asphalt, metals, solder, silicon, interfaces and joints, liquefaction, microcracking and fracturing in the context of the final arrangement analysis, rate of loading effect, thermal effects, and repetitive loading, interface behavior. You found almost the same type of mathematical equation for stress, for joint or interface behavior, in which the material system between the material in the thin layer is also considered to be some composed of solid and purely as they said parts. You can consider both compression and tensile condition in a hierarchical model. You can have creep behavior by multi-component DSC models. All the viscoelastic, viscoplastic or viscoelastic plastic can be included. And laboratory testing and validation are very important factors. I don't go to detail, but we have developed some new laboratory testing devices. And that is maybe in a parameters. There are for a disturbance function, there are 12 parameters. But with these parameters, this model can account for almost all the exhibited behavior compared to any other model. You can read the literature. We have a lot of papers and a book. Validation, we have specimen level and practical boundary level. I'm going to present in the next few minutes liquefaction application for few typical examples. First of all, the liquefaction in the field during Kobe earthquake. This is a soil profile of the near Kobe earthquake. And one of the things it happened is that before and after and during the earthquake, they have measured the shear wave velocity on the northwest part and east-west part. So we use that shear wave velocity to define disturbance. So disturbance D was obtained on by the measured shear wave velocity in the field in the Kobe earthquake. If you plot the disturbance with the time, you can see at the different depths, 1 meter, 4 meter, 16 meter, 8 meter, disturbance plots like this based on the shear wave velocity. At 14.6, it reaches a critical disturbance of 0.9. And that is about the same time they observe disturbance in the field. So this critical disturbance liquefaction compares very well with what happened in the field in the Kobe earthquake. Liquefaction in a shake table test. We used a shake table test by people from Japan, Akiushi. We used the DSC model to analyze the liquefaction in the shake table test, which was finite element method. This was the finite element mesh. And it was instrumented by various accelerometer and pore water pressure measurement. And we consider the pore water pressure at this point, measurement point, and subjected this bottom to the same type of cyclic sinusoidal load as it was done by Akiushi in the laboratory. And we found that at that point, the excess pore pressure versus time, this was measured by Akiushi in the laboratory, and this was computed by the DSC model. And somewhere here, after 2 seconds, liquefaction has occurred. That was observed in the lab. You can plot the disturbance contours during the finite element analysis. This is 0.5 seconds, 1 second, 2 seconds, and 10 seconds. At 2 seconds, almost 0.85 or 0.95% of the sand reached the critical disturbance, and that they measured that liquefaction occurred. At 10 seconds, everything, whole thing collapsed with final liquefaction. In Korea, Park and his, they have do comprehensive monotonic cyclic simple shear experiment were conducted on Ottawa sand and steel interface. Oh, no. This is what we did in the laboratory, liquefaction on rough interfaces. And this is very interesting. The rough interfaces also can liquefy, which is interesting. And sometimes interface material can liquefy earlier than liquefaction in the surrounding material. So effect of the roughness on the interface behavior are a very unique contribution here. And we consider 3 roughnesses: smooth, slightly texture, and moderately texture, and use this device to measure the pore water pressure by putting a transducer here, and the interface behavior was different roughnesses, and measure the behavior in the laboratory. And I don't want to go on the details. There are 2 papers published recently in the Iacmag, International Journal of Geomechanics. You may look at it. It is by Desai and my co-author, Muhammad Al-Yunis. and you can hear shear stress and relative stress we can compare with this from the DSC model. And but only thing I have done here, I don't know which you can read it, but we have compared the three different roughnesses tests and the time for liquefaction in the laboratory, number of cycles of liquefaction, critical disturbance, and time for liquefaction is measured in the lab is 2600 seconds, and in the laboratory and the DSC model 2614. So it was a very good comparison for different roughnesses. Okay. This is liquefaction, and Park et al. Conducted a liquefaction study on saturated Korean sand with different densities, relative density, and confining pressure. And they also found that the number of cycles to liquefaction from the DSC model, for instance, were 18 here for initial confining pressure of sigma 0 prime of 70. And number of cycles to liquefaction in the laboratory stage were 19. So this is a very good, excellent comparison for different relative densities. I think I will, how much time we have now? 2 minutes? Dr. Donatelli?
Yeah, 5 minutes, 10 minutes.
Okay, that is enough. Pradhan and Desai, we presented detailed study of liquefaction around piles in sand by analyzing centrifuge tests for axially loaded pile. The centrifuge test data were performed at the National Geotechnical Centrifuge at the University of California in Davis. And that there are a lot of papers on that. And we took one pile here, which is instrumented with pore pressure, displacement, bending moment, and acceleration. And then we considered one of the piles and subjected there to the loading, axial loading, as in the field. This is the finite element mesh, and this is more detailed finite element mesh. And this is the interface, and 143 element is mostly we consider. So in this distributive concept with the HIS model was used for the sand, which are tested in a laboratory at Davis. We found the parameters. We found the loading condition, the pile, loading condition from the centrifuge test data, and then applied that and computed displacement, pore pressure, everything in various node points and elements. And see, at that 143 interface, the excess pore vector experimental, pore pressure, which is time. And this was measured in the laboratory. Now, interface behavior is very important. I did not consider the detail because with and without interface, there is no comparison of pore water pressure. But with interface as a mathematical model in the finite element, the pore water pressure behavior was comparable to what was happened in the laboratory. And somewhere here, and 0.9 seconds, liquefaction occurred. And these are some comparison between various elements, and liquefaction according to the Seeds method effective stress method and the liquefaction, time to liquefaction according to the disturbed state concept. And you can see that the time to liquefaction by disturbed state concept is earlier than the time to liquefaction by the conventional method, in which liquefaction is identified when initial effective stress is equal by the pore water pressure. So there is a difference between the conventional and between the disturbed state concept. Now, my last example is a laterally loaded pile, which is quite difficult and not much done. It is a laterally loaded pile in the field by Earth Technology Corporation, a company, was done in 1981. And we conducted analysis, Esa and Desai, myself, and my student Muhammad, who is now professor in Iraq, in the Basra, using finite element method and disturbed state concept. Two independent finite element interface and without interface were done. Harmonic sinusoidal wave displacement applied at the lateral direction at 0.61 meter below the pile. And if I will not go into details it is in those papers. This is a pile that the load was applied somewhere here, and this node were placed far distance so that the boundary effect was hardly any. And this is a load displacement curve which was applied in a lateral direction, not axial. Lateral direction is not very easy to find some field experimental data. The finite element in one of the elements, 398, with interface, this is a measured value. And this is without interface, with interface. And this is a pore water pressure measured in the field. So there is a irregularity, but with interface, the pore water pressure is more nearer to the measurements than without interface. Now, when the load was applied at 204 step, one peak was there. There was another peak at 214 step. So we consider the pore water pressure contours at those two subsequent peaks. And you can see that when the load is applied this way, the pore pressure is about 0.5 here. And at 214, it is reverse direction. This whole thing is reversed because the load is applied in the other direction. I will say the disturbance contours at step 1, 2, 4 and 214 is like this. And you can see that around this point here and this vicinity of the pile, disturbance approach 0.9, which is a critical disturbance we defined from the laboratory test. And that is where liquefaction occurs in the lateral load. Figure step 214 and present the disturbance contours at two subsequent peaks. The value of D varied between 0.79, 0.9 immediately around the pile and gradually reduces in the far regions. The critical disturbance value for Ottawa sand, DC is 0.84, and Ottawa sand steel interface is 0.91. It can be concluded that the liquefaction occurs around the pile in the shallow soil and that coincide with the field observation reported by the Earth technology. It made me noted that the DSC allows computation of liquefaction in interfaces also, not only in the soil. Conclusion. Microstructural instabilities identified by threshold states occur in many materials and lead to initial and final liquefaction. Conventional methods for liquefaction do not account for the internal mechanism that lead to liquefaction. The disturbed state concept and energy method, on the other hand, allow for the internal mechanism. It has been found that the DSC, disturbed state concept, with the HIS model can lead to simpler model compared to the energy method because it is easier to compute disturbance and evaluate in computer finite element procedure. Hence, the DSC is described in detail today, including theory, parameter, and validation. Several validations with respect to field and laboratory simulation of practical geotechnical problem are presented in this paper. It can be concluded that the DSC is perhaps, not always, the only fundamental, unified, and easier procedure for liquefaction analysis. It can be used by praxis by evaluating critical disturbance for standard tests and by using computer finite element method. Thank you very much.
Thank you very much, Professor Desai. It was really very interesting. Are there questions in the Q&A chat? I don't see any question, so maybe they are coming. I have a question for you. Well, I'm always very impressed by the versatility of the DSC method. So my curiosity is, among all the geomechanical phenomena that we can study and we can model with this method, which is the most challenging? Maybe because the calibration of the disturbance parameter is too difficult, or for some other reasons?
You know, the disturbance parameters, as I have said in many papers in the book, can be obtained from standard triaxial or consolidation or uniaxial tests. It may be that without disturbance, for continuum method, you find Young's modulus, Poisson's ratio, critical state parameters. For disturbance state, you have to find 2 more parameters, 3 more parameters from the same test. But then what will happen? The conventional method do not provide for the effect of discontinuity, fully volume change, and this kind of liquefaction or instability or microstructural changes. Not only that, I'm talking of soil here, but we have applied this disturbed state concept and many people for metals and soliders in electronics for failure, which is synonymous with liquefaction. And it is not very difficult to find the parameters. Actually, we have a computer program. You can put the stress strain points and it will spit out the parameters. So people have a feeling it is not, Donatella, it is not difficult to find those parameters. Many people now have done it actually. There are so many people have not only applied this for this type of material of soils, but so many other materials that we are in process of putting together a book, this substrate concept, about 35 chapters for different materials in geotechnical, in concrete and structural analysis and composite materials. So it is not, it is just people have that feeling, but it is not difficult.
Okay, thank you. Thank you very much. So we can close this part and we can come to the... Thank you very much, Professor Desai. Hope to see you next year on in presence in Torino. Bye.
I don't know. I hope so. Marco, I will try, but
I hope so, of course. Yeah.
So it has been an intensive 3 hours. Thank you very much to all, to the participants, particularly to the speakers. Thank you, Professor Desai, for waking up early in the morning to deliver this lecture. People from far Asia, they have already gone to sleep now, but they will be able to see your lecture because we have recorded it. So we will try to make it available to the registered Iacmag participants on the website, so that people that lost the first lecture can see them recorded as well as the last lecture, because of course it was very difficult for all of you due to the time zones. Now, I would like to say that here, together with my colleagues of the organizing committee, that we will continue working on trying to organize this conference. And we really hope that we will be able to meet in a year time, in person, of course. So what I would like to ask all is to follow the news, because we update the website. We send some newsletters every now and then. And so just try to follow the news so that you have updated information. I remind that we have decided to open a new call for abstract and papers, so that we can publish another volume, a third volume of the proceedings. And the call for abstract is open, so you can send abstracts and papers. And of course, also share the information around, so we can enlarge the community. So what else? Let's cross fingers that we will be able really to meet in person shortly. And what else to say? Well, thank you again to all the speakers. It was really very much appreciated, because we made this warming up event, but without the speakers, this would have not been possible. And so what else to say? See you soon, hopefully in Italy next year, all together. Bye-bye to everybody.
Thank you, Carrie, and thank you, everybody. And thank you, Marcos, for doing outstanding job.
Bye-bye to everybody.
Thank you all. Bye-bye.
What does TORINO mean? TORINO is like the water of its rivers. An evolving city, constantly moving. TORINO means a community of people, using the city as a living lab. TORINO means ideas, feeding companies and creating startups, traveling fast along streets, data and connections, in a virtuous circle of minds, research and innovation. TORINO means innovative spaces, a city growing stronger, discovering new uses and generating shared facilities. TORINO means culture, surprising heritage and captivating flavors. seducing thousands of people every day. Torino, a city with endless possibilities.